you can calculate incrementally what's happening and track it until the system dies or splits apart or whatever. But you cannot analytically predict the future of the three-body system, because what chaos will do for you in your mathematical model is if you change the initial conditions by a little bit, the solution diverges.
Further down the line, it goes
crazy. It's not just a little bit different later on down the line.
Exactly. It is exponentially different.
Here, we're talking about how a system can be completely governed by physical law and yet deny us a clean, closed-form prediction. That sounds like a contradiction until you look at what chaos really measures. It doesn't say the universe is lawless. It says that the future consumes information. In a chaotic system, tiny discrepancies in the present balloon roughly exponentially as you look farther ahead in time. Mathematicians package that growth in a number called a Lyapunov exponent. Translated into plain English, to see twice as far into the future, you need about twice as many reliable digits. The tolerated fuzz in the starting state must shrink exponentially with the horizon. Every extra day of weather forecast, every extra orbit in a multi-body dance demands more bits of knowledge than yesterday could deliver. So, how do scientists make peace with that? By switching the question. If exact trajectories slip from our fingers, we ask instead, what structure survives? Conservation laws still hold. Energy and angular momentum remain bookkeepers even in the wildest gravitational malaise. Phase space, the mathematical arena of all possible states, doesn't evaporate. It stretches and folds. Liouville's theorem tells us the total volume of possibilities stays constant as it contorts. That's not a guess, it's a guarantee. And when you slice that phase space at just the right angle, what Poincaré did, you see islands of order inside seas of apparent randomness, resonances where motion locks into ratios, separated by swirling layers where trajectories wander. Here's the first twist. Our own solar system contains both. Pluto's orbit looks precarious until you notice it's in a 3.2 resonance with Neptune. The gravitational tugs lock into a pattern that prevents close encounters over billions of years. Meanwhile, the asteroid belt has gaps, zones where resonances with Jupiter kick rocks into new orbits over millions of years. The system isn't a coin flip, it's a chessboard with trap squares. And when you zoom out, the big picture is even more sobering. Numerical studies show that parts of the solar system are chaotic with a Lyapunov time of a few million years. That's the E-folding timescale for the amplification of tiny uncertainties. We can compute Earth's orbit with exquisite confidence for tens of millions of years, but not with absolute eternity. That's not failure. It's the recognition of a predictive horizon. If you want a more terrestrial example, weather gives you a daily demonstration, and the atmosphere has a Lyapunov time of about 2 days. That's why 5-day forecasts are good, 10-day forecasts are iffy, and seasonal climate projections rely on averages, not specifics. A weather modeler doesn't trust one simulation run. They launch an ensemble, many simulations with slightly perturbed initial states, to map the range of plausible outcomes. It's not hedging, it's the honest physics of a system that amplifies small differences. And yet, we can say winter will be colder than summer on average. We can say hurricanes prefer warm water. We traded certainty of the particular for reliability of the pattern. There's a second twist, and it's surprisingly optimistic. Chaos can be navigated. Space agencies exploit it. The restricted three-body problem, 2 heavy bodies like Earth and the Sun, plus a small spacecraft, has 5 special regions called Lagrange points. Around the saddle-type Lagrange points, like L1 and L2, the nonlinear dynamics generate tubes in phase space, stable and unstable invariant manifolds, that act like low-energy highways. Missions like Genesis and Artemis have surfed those highways, using gravity and a whisper of fuel to drift from one celestial neighborhood to another. It seems paradoxical. The same sensitivity that limits prediction opens pathways you cannot build from straight-line intuition. We don't just survive chaos, we architect with it. Let's get quantitative again, because the numbers teach humility. Suppose a system has a Lyapunov exponent LL. To predict out to time t within a tolerance A, you need to know the initial state within roughly ERE Masan LT. And bits of information, that's about LT, ln, 2, extra binary digits. If L is 1 per million years, reasonable for some orbital contexts, Predicting 10 million years requires about 14 extra bits beyond whatever accuracy you started with. That's not much. But if L is 1 per day, closer to the atmosphere, predicting 30 days requires about 43 extra bits. Precision demands scale hard. Measurement noise, thermal fluctuations, even the recoil from sunlight on asteroids, the Yarkovsky effect, become the villains in long-term forecasts. Not because they're large, but because chaos gives them a megaphone. Then there's a theorem with a comforting name, Kolmogorov-Arnold-Moser, or CAM. It says that for many nearly integrable systems, where you start with a perfectly predictable motion and add small perturbations, most of the orderly orbits survive as deformed but intact tori. Not all of them. Resonances tear holes. But the result carves the cosmos into regions of long-term stability and patches of turbulence. That's why Trojan asteroids can lounge at Jupiter's L4 and L5 points for billions of years, while other rocks are flung toward planets or out into interstellar space. Stability isn't an accident. It's a consequence of structure resilient to disturbance. What does all of this mean for how we know? It means determinism isn't the same as predictability. The equations can be strict, and still, our finite measurements and finite computers impose a horizon. Science adapts by focusing on invariance, on statistics, on maps of possibility rather than single destinies. We don't surrender the future, we classify it. We name the resonances, compute the exponents, chart the manifolds, and choose where to aim our spacecraft, or our expectations. And there's a final human lesson tucked in that physics, you're not a planet, but your plans live under a similar rule. Some choices amplify. Small biases today can become big divergences months from now. You won't plot every outcome exactly, but you can identify the stable islands in your life, the resonances that protect you, the highways that open when you nudge in the right direction. Predict less, understand more. That's not lowering the bar. That's raising your aim from certainties you cannot have to structures you can use. Like if this was interesting, and hit the subscribe for more.